Welcome to Chapter 12. Does this make sense? What is the pH of a 1.0 times 10 to the negative 10 molarity hydrochloric acid solution? Okay. That's a really small molarity. Very low concentration. Let's see what we end up with. Step 1, always identify the major species. So in this case, we are working with the ever popular hydrochloric acid, which we should know, is a strong acid. Step 2, what do I do with that information? Write out the reaction. So we have hydrochloric acid forming hydrogen and chloride. Now here's the thing. Because that concentration is so incredibly low, I'm actually going to include water as one of my major species. So I'm going to write it up here, H2O. Weak. It could be either an acid or a base. So here I have my water, and I know that water, you can call it auto-ionization. It auto-ionizes into hydrogen and hydroxide. Now again, if you're not sure why I'm doing that, you should be able to see it once we start crunching some numbers. So step 3, this is the last step, isn't that nice? Solve for the pH. Let's deal with HCl first. So I know, well, first off, it's strong, so do I need to make an ice chart? No, I do not. Has it been diluted? Do I need to do a dilution? No, I don't. It doesn't say anything about a dilution. So I know the concentration of the entire compound, and I know that there's one hydrogen for every hydrochloric acid compound. So I have 1.0 times 10 to the negative 10 is the concentration of hydrogen. And I also know that it's a 1-to-1 for the chlorine ions as well. So okay, so now let's talk about water. Water is always there, and technically you could always throw these numbers in for water if you would like. We know, this is on the side, you don't need to write it down. We know that the Kw for water is the concentration of the hydroxide times the concentration of the hydrogen. It's always equal to 1.0 times 10 to the negative 14, which means that, and we know that they're in water, just water by itself, they're equal. So we'll have, because water is basically neutral. Basically neutral. Funny. All right, so we end up with these concentrations for water, just water. Oops, that should be a 7. Okay, so if that's the case, I can record that over here. So 1.0 times 10 to the negative 7 is my hydrogen from my water autoionization and my hydroxide. Okay, so here's the thing. Look at the concentration of your hydrogen ions. We have 1.0 times 10 to the negative 10 and 1.0 times 10 to the negative 7. So here's a cool annotation for you. If the concentration of an acid or base, here I'll write it down. If the concentration of an acid or base is small, and we're talking less than times 10 to the negative 7, then the majority of your hydrogen ions is actually going to come from your water, from water's natural process of forming hydrogens and hydroxides. So I would recommend that you write this down somewhere, even if you've already gotten as many annotations as you need to fulfill my requirements. Okay, so now let's actually figure out that pH. I'm going to add together my two pHs. So, not my two pHs. I need to add together my two concentrations of hydrogen ions. So that'll give me, okay, 1.0 times 10 to the negative 10 plus 1.0 times 10 to the negative 7. And if you want to keep only one digit after the decimal place to follow addition sig fig rules, this actually ends up just being equal to 1.0 times 10 to the negative 7. So, okay, I know that pH is equal to the negative log of the concentration of my hydrogen ions. And if you plug that in your calculator, you end up with a pH equal to 7. That's right, you have a container full of diluted hydrochloric acid, and it actually ends up being neutral, effectively neutral. Now, if I didn't follow the sig fig rules, I would have ended up with 1.001 times 10 to the negative 7 in here. And if you took the negative log of that, you would have ended up with like 6.99999 or whatever. And that is very, very, very slightly acidic. But as we know, sig figs don't allow for that. So you end up with 7. So, does this make sense?